Ni hao. Hello. This is the 10th lesson in heat transfer. In this lesson, we will look at arrays of fins. Arrays of fins are sometimes called heat sinks. In this lesson, we will look at how to analyze heat sinks using a thermal circuit model. By the end of this lesson, you should be able to calculate the total area of an array of fins. You should also be able to calculate the overall surface efficiency of an array of fins. Finally, you should be able to calculate the thermal resistance of an array of fins and incorporate that thermal resistance into a circuit model of a physical system. On with the lesson.
Okay, then I actually want to move to an example because we're in a position now to start thinking about how to take that work that we did for one fin and apply it to an array, right? A couple of things to do before then, but I think it's helpful to put this in context a little bit. So here is an actual problem, one that you could encounter for sure. So we have a chip, all right? It's a square chip that we're trying to keep cool. It could be a chip on a computer or a microcontroller. But this is problem 350, by the way. This is from your book. So this is 3150, if you want to look at it later. So this is the chip down here. It's at the bottom. And we're just told we want to keep this chip it's going to be at one temperature. And we need to maintain it at some temperature or below that temperature in order to make sure it works. And we're given that temperature. Okay, so this whole thing is all one big temperature TC, and that TC is given to us as 85C. So there's kind of two possibilities. One, we could just put the chip and let it cool to the ambient, right? No heat sink on it. That's one possibility, and we could calculate that one pretty quickly because we're given the convection heat transfer coefficient, and we're given the fluid temperature that it's convecting to. So we could just calculate it, right? It'd be HA T minus T infinity, where T would be the chip temperature. But you'll see you're gonna end up with dissipating a lot less energy, right, than if we could put the heat sink on. And that's what's attached on the top. But when you attach the heat sink, you also take on an additional resistance because of the contact resistance between the chip surface and the base of the heat sink. That's what this interface is, and this contact resistance. And then the heat sink is sitting on top. And the heat sink does have some resistance to heat transfer, right? So you're also adding that resistance on. So the question is, are you going to end up with a net reduction because you're increasing the area, all right, a lot more, right, by having all this extra surface for convection heat transfer compared to when you just had the chip. But just something to note is that the way that this problem is drawn, you see the base of the heat sink, of course, this is one solid piece of material, right, where you can almost imagine creating this heat sink by cutting it on a mill, right? And your mill cutter would just go through in passes. It's really easy to make the heat sink that way, and then it would come back and cut back this way, back and forth to make these square fins. And so the place where the mill cutter comes down this deep, and it leaves this base, and the problem is kind of drawn that. So what's important to recognize is that in our work for what we call the base of the fin, that's right here at this interface. So this would be TB right here. And so there is some conduction resistance as well in the solid chunk of material at the base of the heatsink. But even though that's still a heatsink, we separate that away from our array of fins, right? Okay, with that said, you should be able to do this pretty quickly. I want you to draw the thermal circuit, right, for all the parts except for the array of fins. So if you had to apply a thermal circuit to analyze the heat transfer away from the chip, right, just try to draw the circuit up to TB.
Now, what I would like you to do is pause the video and write down an answer to the question.
Okay, I think everybody's back. Aaron asked the question, do we need, just a quick thing, I didn't see this before I put you in rooms, but Aaron asked, do we have to know how to use the hyperbolic sine and cosine functions before the exam on Monday? I don't think so. I'm pretty sure not, but let me look before I say definitively. Okay, Aaron, so remind me on Friday if I don't say so definitively, but I'm thinking no. Okay, so hopefully if you, the circuit that you drew with your partner looks something like this one. All right, there are two resistors, one to model the contact resistance between the base of the heatsink unit and the chip. That's given by that specific contact resistance divided by the area. The other resistor is for the conduction, right, through the material in the base, up in the kind of the bottom of the heatsink up to the base of the array of fins. That's given by LB over KBA. So and the KB here would be just K. I don't know why I put KB. It's the same material everywhere. It's just KB, right? Oh, dang it, just K. This is just K. It's the K of the heatsink, okay? So wouldn't it be nice if we could just, like, I kind of drew another node for the fluid temperature, just to point out, like, it would be really nice, right, if we could just model, right, the whole array of fins as another resistor, yeah, and just have another resistance that we would put in here, right, to represent the heat transfer from the base up to the fluid. And the good news is that we can, okay, I have to kind of try to convince you that that's the case, but we're going to be able to just put a resistor in here, and if you want to just add it for yourself now, and then we'll work out what all the pieces are. But this is going to end up being look like this, okay? Times H times A T. And later on, I'll go through more carefully what these terms mean, right? But if you want to label them now, this is the total area for heat transfer through the array of fins. So what do I mean by that? That means it's all of this area, including the area between the fins, all of this. This is AT, all of this area. I could keep going all the way along, okay? That's AT. And this is something called the overall surface efficiency of the array of fins. So this is the overall efficiency. And for whatever reason, this community decided to call this an efficiency for reasons passing understanding, but I have to use the word even though it pains me to do so. It's not really an efficiency, but okay, we're going to call it the overall efficiency of the heatsink. All right. So I'll try to go through now, and we'll break this down to see how we can get to this resistor, but I thought it would be nice to put it in context to say we could treat this as a resistor. So I'm just going to tell you, there's going to be quite a bit of work, right, to quantify the resistance, but it can be quantified as a resistance in the end. Okay. So the approach to this is essentially to take advantage of kind of the mathematical simplicity of the fin heat transfer rate for the adiabatic tip condition. So if I go back to table 3.4 and I look at the fin heat transfer rates, we're really trying to figure out, right, what's the heat transfer rate through these fins? If I can figure out one of them, you can maybe think like I can figure out what's going on with all of them if I can figure out one of them. So the infinite fin case is overly simplistic. We can't use that one as a good model. But the convective tip, like you look at this equation, this thing is a nightmare. My God, it's awful. Like I don't want to go there. Okay, too complicated. And the prescribed tip temperature is also not very realistic, and so it's difficult to use this one. So if I have to pick between those two that are left over, basically as engineers, we said that one looks like to be a reasonable balance of mathematical complexity and physical reality, okay, accuracy. And so we essentially take this solution, right, which has the fin length in it, L. That's how long the fin is, and we apply it. Even though we know there's heat transfer off of the tip, we're going to apply the adiabatic tip case. The way that we're going to get out of this is we'll say, okay, yeah, we know the tip's not actually adiabatic. So the way we'll get out of it is we'll define a new fin length, and we'll make the fin to be just a little bit longer than it really is. in order to account for this missing heat transfer at the tip that we neglected with the adiabatic tip case, right? And we'll get that in what's called a fin efficiency. So, where is my... Okay, so here's the book. Hopefully you can still see this. Am I still screen sharing? Okay, so in table 3, where are you? Here we go, table 3.5. This is going to be your table to get something what's called the fin efficiency, right? We'll get this labeled down here in a second. But this is the fin efficiency, and I want to go here right now because you see this tan HMLC? That looks a lot like, right, the M tan HML from case B in table 3.4, and that's exactly where it comes from, right? The difference here is that we have an L sub C instead of L sub F for the fin. And if you go over, what's nice about this table is everything is defined for you. So you go over to the left and you see this L sub C, and it's L, which is the fin length, plus something extra. Okay, so this is the out. This is the extra thing. So it's like, we're going to make the fin in, a little longer in order to account for the fact that we're missing the adiabatic tip. We're missing the heat transfer there. So we'll just make the whole thing a little longer and it'll work itself out. Does that make sense? So that's where that comes from. Okay, so having said that, so now let's go in here and talk about what these things are. So we have essentially two things. We have this single fin efficiency, which is that eta sub F that you saw. Okay, so the eta sub F is defined as the heat transfer rate through the fin relative to the maximum possible heat transfer rate you could have through the fin. And I'm going to just try to convince you why this is the right equation for the maximum possible heat transfer. So imagine for a moment, right? If you were a designer, you wanted to pick a material for the heat sink, right? What do you want to have, a superconductive material or a not so conductive material? It's a conductive one, right? Like you want to have a conductive material. Okay, so take it to the extreme. So imagine that you have a conductive material that's infinitely conductive. Its thermal conductivity is 1 bajillion, right? What's the impact of that on the temperature in the heat sink? If you have a 1 bajillion, or a material with 1 bajillion thermal conductivity, 1 bajillion watt per meter Kelvin, what does that mean for the temperature, right? In any individual fin within the heat sink, what temperature are all the fins?
Same.
They're all the same for sure. Okay, so the super high conductivity tends to spread temperature out and even it all out. So then the question is, what temperature is it? So if you remember yeah, Chase?
The temperature of the surroundings.
That's a good thought. That's for sure a good thought. And that's one possibility for sure. But I don't think it'll be the temperature of the surroundings, because we fix the temperature at the base as TB, right? And we have the fluid flowing over this thing on the outside. So imagine if the thermal conductivity here goes to infinity, is it going to take on the surroundings temperature where there's a convection resistance between the fluid, right, and this surface? Or is it going to take on the temperature of the base? It's going to take on the temperature of the base, right? So I know exactly where you were coming from, Chase, and it was a great thought. But the reason that it's the base temperature is because there's a resistance still between the fluid and the fin, because there's convection there, right? So we end up with just every single fin with an infinite conductivity as being at TB. So the entire fin is at TB. So if you look at all of the places, right, on the surface of the fin, and we want to look at the convection there, right, locally, the convection is equal to H now times TB minus T infinity. And that's just equal to theta B by definition. So the maximum heat transfer we can have is this case, right? It's never going to get, we're never going to get any more heat transfer than this. This is the maximum it can possibly be. This is an infinitely conductive fin. And the effect of that is to spread that base temperature out over the entire fin surface. In reality, with a finite conductivity, we expect the temperature to decay, right, from the base temperature down closer to the fluid temperature as you move away from the base along the fin axis. And that, of course, hurts us because now we don't have as large of a delta T to convect into the fluid with. And so our heat transfer rate goes down. So this fin efficiency, okay, accounts for this. This is a number between 0 and 1, this eta F, okay? So you're going to have a number between 0 and 1 for the single fin efficiency. If you had an infinitely conductive fin, you'd have a fin efficiency of 1. If you have a no conductive fin, which is also impossible, you have a fin efficiency of 0. You're going to be somewhere in between depending on how the fin is, the geometry of the fin, basically, and its conductivity, and its thermal conductivity. All right, so we combine that together, that fin, single fin efficiency with the single fin thermal resistance. So this single fin thermal resistance is the thing that's going to be kind of, in the end, more useful to us. And we basically say, okay, we want the thermal resistance associated with a single fin. How can we get it? By definition, we want this to be a delta T, the potential for heat transfer relative to the actual heat transfer. So if this is 2, all we're going to do is take now our work up here in 1 and substitute it into this definition, right? So I have a theta B on the top divided by eta F H A F theta B, and the theta B cancels. So the single fin thermal resistance is just 1 over the fin efficiency times H times the area of the fin. So if you look at this, it looks kind of like a convection resistance, right? It has 1 over H times an area, but there's this extra term, this fin efficiency, right? That accounts for the fact that there's more going on here than just the convection. There's also this conduction on the inside of the fin material, but we lump it all into this fin efficiency. That's a single fin, okay? But we want to know what's going on with the the entire array of fins in our heat sink, right? So there's a way to handle this. And I want you to just, I'll try to explain kind of where this comes from, but we're gonna think of this array of fins, right, as a single resistor, right? Where we're moving energy from the base temperature out to the fluid. So I've got some heat transfer through this heat sink, and we want this to be a single resistor, and it's labeled RTO in your book. O for overall, okay? O for overall. So I'm just going to tell you what this definition, then I'll try to explain where it comes from, okay? So the overall resistance looks sneakily like the single fin resistance, all right? We swap out the single fin efficiency for something called the overall surface efficiency. And we swap out the single fin area for the total area, all right? So this is the overall surface efficiency. Again, efficiency in quotes, it's not really an efficiency. And this is the total area of the array of fins. Those are just definitions. I'm just going to tell you how you calculate these two things, right? You get the overall surface efficiency. It's related to essentially the ratio of the area associated with the fins and the area at the base of the array where there's no fin on the base, okay? And the single fin efficiency. Okay. So this is how you calculate the overall surface efficiency. You need, N is the number of fins. number of fins in the heatsink. Okay, area AF is the area of a single fin, AT is the total area, and this is the single fin efficiency. Okay. The total area of the array we get by calculating the area of the base, which doesn't have fin on it, right? So this is like the spaces between the fins. And we add up all of the surface area associated with the fins. Okay. So this is the area on the surface between the fins. Okay, the way that you get here, right? The way that you get here is we treat the heat transfer through the fin and through the base like a parallel circuit, right? So in essence, we say, okay, we've got a parallel path for the heat transfer from the base out to T infinity. It can either, okay, go through all of the fins, all of the single fins, H, A, F, or it can go through the base. That's an A. Okay, when you analyze that parallel circuit, you get here. So don't bother with this one, okay? Just use this one, but just know that that's where this comes from. It comes from analyzing this parallel path for the heat transfer. Okay. Any questions on that? So these are, right, the main takeaways. Okay, so now we go back to our example problem, and I'm going to let you work it now on your own or in with a partner. Anytime that you have a heatsink problem or an array of fins type problem, like what we have in this example problem, when you go to calculate the array of fins resistance, you're going to follow these 9 steps every single time. If you follow these 9 steps, you're going to get the fin resistance calculated correctly. It's a lot of work to calculate the fin resistance. It looks simple, 1 over A to O, H, A total, but there's a hell of a lot of work that goes into calculating the overall surface efficiency and the total area of the array of fins. Okay? So follow these 9 steps. I'm going to let you try it. I'm just going to talk through it quick and then let you go for it. Okay. The first thing, you want to sketch a single unit of the fin array. What I mean by that is you look at the heatsink geometry and you say, this is just like a repeating structure, right? It's like a fin with some exposed surface around it that's repeated over and over and over again. You have to go in and find the single unit. However, you can do that for yourself. It's important that you can find it and see the single unit. This is almost like in material science, right? When you had unit cells and you looked at crystals as just repeating unit cell over and over again. It's the same idea here. So our unit cell has one fin in it and the area between that fin and its neighbors. Okay. So find the single unit and sketch it. It's really helpful to sketch it to me. Then you label the geometry. So you label whatever geometry is associated with the fin. It could be a diameter, it could be a side length, and the whole unit is going to have some length on its side. Right? And a lot of times the length of the whole unit is going to be given by what's called the pitch of the heatsink. The pitch is the spacing between the fins plus the fin, right? It's like it's how many fins we have per unit length. Okay. So you're going to label geometry. Then once you've done that, once you've identified your single fin unit, you're going to figure out how many units you have in the array. And the most important thing here, your book is going to give you a picture. And in fact, we get a picture associated with problem 3150. You can't trust the picture on how many fins there are. So you're gonna go calculate in this example problem the number of fins. You're gonna see that there are way more fins than what you would think there are based off of the picture. So don't count the fins in the picture and think that's an accurate representation of that problem. Okay, always follow these steps. So the way you get the number of fins is you take the length of the fin unit in one coordinate direction and you divide by the overall length of the heatsink in that direction. That's going to give you how many units you have in that particular direction. If there's a second direction, like there is in our problem here, we repeat that step for the second direction. That'll give us the number of fin units in one direction and the other direction, right? So it's like 2 sides of a table. If I want to figure out how many things are on the table, right, I take the length of this side and the length of this side and I multiply them together. and that gives you your total number of fins in your array. Okay. Once you've done that, you have to figure out the total base surface area, the AB in the A total definition. And for me, it's often easiest to do that, right, by I look at the heatsink from top down, and I take the overall area, just the area that I see when I look down, the total thing. For us, it's a square. I get that area and I subtract all of the cross-sectional areas of the fins, right? That's just going to leave me with the base area left over. Does that make sense? So I look at a top-down view of the heatsink, and what I see is the cross sections of the fins and all of the area in between. So if I want to get all the area in between, I take the overall thing and I subtract all the little cross-sectional areas. That gives me what I want. That isn't going to be universally true that that's the easiest way, but most of the time that's the easiest way. Then you're going to go to table 3.5 and you're going to get the single fin area. You're just gonna, it's listed right in the table. Don't try to memorize anything. Don't try to figure it out on your own. Just go get the freaking equation from the table, okay? Minimize thinking. You've got enough thinking with the 9 steps, yeah? You just go look up the equation for the single fin area and you calculate it. Then you can calculate the total surface area of the array. You take your base area from step 4 and you add in the single fin area from step 5 times the total number of fins from step 3 and you get your total area. Done, okay? Now you're gonna go work on your efficiencies. So go back to table 3.5, or there are gonna be some helpful figures for circular geometries to get the efficiency of a single fin. You'll be able to just calculate it. Okay? Once you've got the single fin efficiency, now you've got all the pieces of the overall surface efficiency. You need the total area, the number of fins, the single fin area, and the single fin efficiency. You calculate it, and now you've got all the pieces of the resistance, the overall surface efficiency, the convection coefficient, and the total area of the array, okay? So go for it. You've got the example problem. Try to walk through these 9 steps.
Now, what I would like you to do is pause the video and write down an answer to the question.
Okay, so let's, I know some of you are still kind of crunching the numbers, which is okay, but I think most of you have gotten through what I think is the hard part, which is doing the geometry. And it looks like you all got it right. So this solution is posted on Blackboard, and so you have access to it later, but I'm just gonna walk you through the steps now of analyzing, or getting this thermal resistance. So this is our circuit, which you should have sketched on Monday, right? We have 3 resistors. To solve the problem, we'd actually have to calculate the values of the resistance for the contact resistance and the conduction as well. I'm going to focus on the fin array this time. Yeah, Daniel.
Is M unitless?
M is not unitless. It should have units of inverse length. When you multiply by L, it should become units. So just walking through the steps, here's my first step. This is my sketch of the single fin unit, right? It looks like a square. It has area between the fins and the fin in it, and the length of the sides is the pitch. So there are WC over S units in each direction, and I think all of you got to 1024. Okay, so 32 squared fins. And if you look at the picture, right, way fewer than 1024 fins in the picture, which is why I say you can't trust the pictures. Okay, so you always want to follow the steps. To get the base area, I followed my approach and I looked at the total area, which was just WC squared minus N times the cross-sectional area of a single fin, which was just little w squared. So the base area I calculate was 1.92 times 10 to the minus 4 square meters. So then you go and you work on the area of a single fin. I just followed I've just followed blindly, okay, table 3.5 for how to calculate the fin area. In this case, you probably could get it, right, because it's a relatively simple geometry. But because I knew I was going to need LC later, I just followed what table 3.5 said. And it said, if you want to calculate the fin area, take 2 times the side length times L sub C, and L sub C was the fin length plus the thickness of the fin half. The thickness is the same as the width in this case. So it's a half of 0.25. So I get the single fin area is 3 times 10 to the minus 6 square meters. So then I am in a position to calculate the total area of the array. Take my 1,024 fins times the area of a single fin, and I add in the area of the surface that's not covered by fins. And I just note that if you look at the numbers, right, most of the area for convection heat transfer is on a fin, not in the area between the fins, by about a factor of 10, right? So 10 to the minus 4 square meters on the surface, 10 to the minus 3 between. Now we can go do the overall, well, we got to get the single fin efficiency next. So I calculated my M as 245 per meter. And then I already have LC from my step getting the fin area. So you put that into the fin efficiency equation from table 3.5, which was the hyperbolic tangent over MLC. My single fin efficiency was 0.6. I could take that then and plug it into the equation for the overall surface efficiency, which required the number of fins, the single fin area, and the total area that I calculated from previous steps, plus the single fin efficiency, and you get an overall efficiency of 0.626228. So now you could go in, all right, and with the other resistances that you already know how to calculate the total resistance of that circuit, and thus calculate the heat transfer rate, okay, from stuff that you've seen before. So just as a real quick, just to say, we got 163 watts of dissipation with the heatsink attached. Without the heatsink, we just have convection, and you only get 23 watts. So the heatsink, even though it adds a contact resistance between the chip and the heatsink, you still get a huge increase, right, in the heat transfer rate because you've increased the area so much for heat transfer. Plus, it was a copper heatsink in this case, so the fin efficiencies were high.